Buoyancy Basics. So, buoyancy, that is the force of a fluid on something else to buoy it up. So we have a container of water with an object in it. It was found by Archimedes a long time ago that the force on this thing comes from the water, of course. Remember, in modern terms, Archimedes didn't know it, but later on, Newton, second law, F equals ma, third law, forces come in pairs. So this is pushing on the water, and the water is pushing on it. The forces are equal. F1 equals m2. So then ma equals ma. Mass times acceleration is mass times acceleration. The forces come in pairs. Again, it's pushing on the water is pushing on it. Then in this case, what's relevant is density and volume and stuff. So here, and a causal factor going on in this situation and making it happen is gravity. It's driven by gravity. Things being pulled down and pushing on other things. So just like a balloon going up, you got a balloon in the air, the string, let go of it, it goes up because it's being buoyed up. There's density as a causal factor, and the pressure of a fluid on it. So air pushes on this, water pushes on this. So here, G is a factor in both cases. You got the weight of one thing. Remember, density times volume is mass. Mass times acceleration. Mass times acceleration. This is another mass times acceleration. So rho Vg is rho Vg, ma. Water is pushing on this. How much water? However much this is pushed out of the way. So here, there's only this part of the water or milk, this volume in red has been pushed out. So that's the volume of water relevant to pushing on this thing. So a volume of milk is pushed out of the way. The density of milk times this volume is the mass of milk relevant. And that mass times G is the force acting on this thing. Okay? What's relevant is like how much fluid is displaced. How much air is displaced by that balloon pushed out of the way. So here, the whole thing is in the water. So the whole volume, the density of water times that volume would be the mass of water displaced. This volume times density of milk would be the mass of milk displaced. So, and that's the part that does like the pushing on the thing, gives buoyant force. Okay, so buoyancy, the force on the thing, because F equals ma and forces are balanced. Hence, rho Vg is rho Vg. So if we have a block of lithium of these dimensions is placed in a container of milk right here. If there were no chemical reaction, calculate the buoyancy force on the block. Here's our block. How much is the milk pushing on it? And calculate the percent of the volume of the block immersed in the water. What percent is that of the whole thing? Remember, percent would be part over whole. It's like a fraction converted into a percentage. A percent is nothing more than a fraction with a denominator of 100. So what we're gonna do, we get this, notice G is the same in both cases, divide it out, rho 1 V1 is rho 2 V2. And then if we write that in terms of milk and stuff and lithium, I'll say instead of a 2 here, I'll say M for milk. And then we got, if 2 is the milk, and we divide by this, so rho lithium over rho milk. Volume of the lithium. So we got milk, milk, lithium, lithium, divide. Okay, so lithium over milk. Cool. Then put our numbers in. The density of lithium from a table I'll link to is about 0.534 grams per cubic centimeter, and that's going to be, when you do the conversion into cubic meters into kilograms, it's like multiplying by 1,000. So 534 kilograms per cubic meter. And density of milk, it's 1.03 gram per cubic centimeter, multiplied by 1,000, 1,030 kilogram per cubic meter. And then the volume of lithium is here. We got 0.17 times 0.14 times 0.3, 0.00714 cubic meters. And so we do that times 534 divided by 1,030, and we get 0.0037. Okay, that's how much milk is displaced. So if you draw a diagram, it helps you think. That's the volume of milk displaced, and that's the volume of lithium in the milk. The rest of it is out of the milk. If this much is in the milk, this minus this is how much is out of the milk. So it'd be like 0.00344 cubic meters would be out. So a little more is in the milk than out of the milk. And that makes sense because this is a little bit more than half. A little bit more than half of the thing is in the milk. A little bit less would be out of the milk. Okay? This fraction of this is in the milk. And so the ratio of block in the milk would be this volume compared to the whole thing. And so we got 0.0037, 0.00714, 0.518. So 51.8% is in the milk. And 48.2% is out. That's what it asked for, but I'll do that. That'll make sense of it. So it's about 50-50 in and out, a little more in, then a little bit less of it out of the milk. So there is percent of the volume of the block immersed. And there's the Y. Now, calculate the buoyancy force on the block. And so we need to bring our G back into play. Ooh, my screen went dark. Undark my screen. Okay. So for that part, we're going to have, we could do either one. We could have done this right away with the lithium and stuff. Or we could do this. It'll be the same thing. So the buoyancy force is just density of lithium, volume of lithium times G, which would be the same. And that should be the same. We should get the same thing if we do this, and this should be the same. So density of milk, volume of milk displaced times acceleration due to gravity. We'll see if we get the same thing. So in one case, let me erase this. I need the volume, I need that. So let's see, so we should get 534 times, what was that? Where'd it go? 0.17, clear, craziness, 0.17 times 0.14 times 0.3, yeah, 0.0714, right there. Should have remembered that. Times 9.8, and that should equal density of milk, volume displaced, acceleration due to gravity, should be the same thing. And so we got 534 times 0.00714 times 9.8, 37 point, we'll make it 37.4 newtons. And then over here, 1030 times 0.0037 times 9.8, enter. Same thing. 37.3 will make it. So, 37.3 newtons. That is the buoyancy force of the milk on the lithium block. The milk buoys up the lithium block. So there's one buoyancy problem, Buoyancy Basics 1. Then I can do a separate video with something immersed in the water, held up by a string or something. A little more analysis involved.